welcome to the laureate lectures. This year we have one lecture per discipline, so one in mathematics, one in computer science. The lectures will be 45 minutes live with 15 minutes Q&A following. I would like to remind you that already during the lecture you can submit questions in the conference tool just next to the video. You have Slido and you can write your question and also like up questions other people ask. So it's now my pleasure to welcome Avi Wigderson, the recipient of the Abel Prize 2021, jointly with Laszlo Lovász, for their foundational contributions to theoretical computer science and discrete mathematics, and their leading role in shaping them into central fields of modern mathematics. Avi has actually been at the Heidelberg Laureate Forum before because he is also the recipient of the Nevanlinna Prize 1994 on his work on computational complexity. Today, Avi will tell us about the value of errors in proofs and take us on a fascinating journey from Alan Turing to recent scientific breakthroughs. It's wonderful to have you with us, Avi. Please, the floor is yours.
And I'm not seeing anyone, but I hope you're all there, and thanks for coming. I want to tell you about the value of errors in proofs. I will explain everything in blue, in particular the quantum nature of this recent breakthrough, but let's start at the beginning. So the plan is simple. I want to tell you about the value of introducing errors into proofs in several fashions. It impacts science and technology a great deal. I will not talk too much about this. I'll mention it. It has very conceptual impacts that I'll talk about, some paradoxical properties that proof systems can have and some impact on math, and get to this breakthrough at the very end of the talk. But before telling you about errors in proofs, I have to talk about errors in computations. And before that, I'll just discuss proofs and computations. More than anything, I really want to talk about the value of the computational complexity methodology of modeling, organizing problems, classes of problems by algorithmic efficiency. You'll see it throughout the talk. It's a story of the evolution of proof systems according to these principles. Any of you who want to read more about this or read more about computational complexity are welcome to look at my book, which is free online. So let me start with proofs and computations. Just give you 2 points in a very long history. The first is like a couple of millennia ago. The elements of Euclid tell you how to derive many theorems in plane geometry by deduction from 5 simple axioms. So these are proofs of theorems. But if you look at them, all of them are actually constructions of planar point sets using straight edge and compass. So they are actually computation with very simple operations. So here in plane geometry, proofs and computations coincide. If we jump to the turn of the 20th century, we get to Hilbert's dream that I'm sure many know about. He believed that truth in mathematics is the same as provability, and he also believed that everything provable is computable. Well, this dream was shattered first by Gödel's incompleteness theorem, showing that the first equation is wrong, and then by Turing, showing that the second is wrong. And I want to talk about the second, about computation and proofs. The way Turing did it, or his first step, was actually to define algorithms using his Turing machines. As we all know, that led to the computer revolution. People started building computers immediately afterwards. I should also point out that this paper was written he was a graduate student, so it should inspire all of you graduate students and postdocs. But I don't want to talk about this. I want to talk about theory. And so what do algorithms compute? They compute, in this talk, decision problems. Every set S, a set of numbers, set of graphs, a set of sequences, defines a decision problem. I give you a number, a sequence, a graph, and ask you, is it in this set? That's what we want to understand. And then you can define two classes, which Turing did. All sets computable by finite algorithms. That's the computation side. And RE, these are the sets provable to finite algorithms, or in other words, verifiable by finite algorithms. And his major theorem was that these two are different. That was shattering the second Hilbert dream. We in computational complexity care about efficient algorithms. So many of you have heard of P and NP, and they have the similar definitions. P is a set of, collection of sets computable by efficient algorithms, and NP similarly sets provable to efficient algorithms. Efficient for this talk, and the most common use is means polynomial time in the size of the data x. There are other definitions that are studied, but we'll stick with that. Of course, here we don't know the answer, whether these two sets are the same or different. That's a major question of computer science and, in fact, of mathematics. I want to start by giving examples of, just to start understanding both intuitively and formally the notion of proofs, arguments, proof systems, provers, verifiers, so on. So basically, you want to understand we'll explore what is the nature of a convincing argument. So this is some claim that some element is in some set. And there are two parties here. A verifier that's really eager to know the answer but is limited, perhaps cannot compute it on its own. And a prover who is trying to help by supplying an argument, but the verifier is not going to trust the prover. The prover is infinitely clever, can do anything, but, you want to verify that he's not just fooling you. Here's an example, and these examples will be examples of proof systems. Here, claims are of the nature a certain number is a composite number. An argument for it will be two smaller numbers, and the verification is just you multiply these two numbers and check that they give you the input, and reject or accept accordingly. Of course, that's a very efficient algorithm, just multiplying two numbers, simple arithmetic. And of course, this system is general. It works for any number, not just this particular one here. And this proof system produces a set of theorems, everything acceptable by this verification algorithm, which is a set, in this case, of composite numbers. I want to stress that in proof systems, generating the argument, the complexity of that is, not interesting at all, only complexity of verification. We know from, the fact that the world assumes factoring is difficult, that maybe getting the argument is hard. We don't care about this. We care about verification being efficient. Here's another example, Sudoku puzzles. Claim is that this puzzle is solvable. An argument will be just filling the empty squares, and verification will be just checking that it complied with the Sudoku rules. Again, very simple algorithm, efficient. And the set of theorems produced by this proof system are all solvable Sudoku puzzles. This is general, and not just general for such small examples. Of course, you can generalize the Sudoku rules to any size board. So also here we have infinitely many theorems and infinitely many non-theorems. Back to familiar deductive proof systems like plane geometry and Euclid, we have the piano arithmetic. In these deductive systems, we have a bunch of axioms. We have deduction rules like modus ponens here, and an argument for a claim, which is a formula or expression over integers, is just a sequence of other formulas. That the last one is supposed to be the claim, and the verification again is very simple and efficient. You just check that each formula in this sequence is either an axiom or follows from previous ones by deduction rule. And in this case, we have maybe more interesting theorems than Sudoku puzzles, like that there are infinitely many primes or Fermat's last theorem and so on. But it's of the same nature. So let's generalize now and see what we understand about essentials of proof systems. They have two properties that are critical: completeness, that true claims have proofs, soundness, that false claims don't have proofs. You can't be fooled. And the arguments are easy to check. It's easy to distinguish convincing and faulty arguments by this verifier. Again, efficient will mean polynomial time in the length of the claim. Encapsulating this formally is what computer scientists, complexity theorists like to do, and here it is. It was done the 70s by Cook and Rechow. What is a proof system? Of course, everybody knows that in math there are zillions of proof systems. We want to have just one definition. So, as we said, the critical object there is a verifier, which is supposed to be an efficient algorithm. It takes two inputs, a claim and an argument, and should satisfy these two conditions. Completeness, if the claim is true, then some argument makes it accept. This is a happy case where the claim becomes a theorem, the argument becomes a proof. And soundness, if the claim is false, then for every argument, doesn't matter which, the verifier will reject. For any such proof systems, like we saw in the examples, it collects the set of theorems, set of whatever the verifier accepts. We call it T sub V of this verifier. And it's a very simple theorem to prove that what you get when you look at all possible deterministic verifiers, this collection of sets is actually the class NP. So if you haven't seen a formal definition of NP, here is one. And we have the sets there include the solvable Sudoku puzzles and the composite numbers and the sets provable in piano arithmetic and so on. The class P sitting inside it is the class of all problems for which you don't need the argument. You can compute test the claim on your own in deterministic polynomial time. Okay, that's classical proof systems. Now we are going to introduce errors into proof systems. So before that, I want to show you, and you probably know, how they are introduced into computation. So one slide background, probabilistic computation and errors. The basic assumption is that nature is benevolent and gives us access to randomness, to unpredictability. And if we have it, let's let algorithms make random choices. So what's a probabilistic algorithm? Well, a deterministic algorithm is one that never errs, right? It computes a function. If for every input, what it outputs is the function value. A probabilistic algorithm using random choices outputs a random variable. So what we demand is instead that for every input, it will output the correct value with high probability. High, let's say, probability 2/3. So we introduce errors in algorithms. Here we allow the error to be 1/3. And you may complain that this error is too high, but the value of this definition is that errors can be reduced arbitrarily just by repetition. If you have an algorithm with 1/3 error, you can run it k times. K can be anything you want. And take a majority vote of the answers. This reduces the error to being exponentially small in k. So that's a robust definition. What's the value of errors in algorithms? Well, we know it seems to solve many, many more problems than deterministic algorithms, as far as we know. That's how it seems, at least, to us. And of course, the rationale for allowing it as, we assume to have access to this randomness, and we tolerate uncertainty everywhere in life, so why not in algorithms? That seems seems to have been a very important step. Well, ancient, of course, but formalizing it in the last 50 years has been an extremely important development in using computers, allowing algorithms in them. What we are going to do now is import this definition from algorithm, from computation to proof system. So we are going to introduce errors into proofs. First of all, this was done in the seminal papers in '85. Given the way we have defined proof systems, it's very easy to introduce randomness to them because they are defined by an algorithm, the verifier. So we simply allow the algorithm, the verification algorithm, to be probabilistic, and we allow these conditions, completeness and soundness, to be satisfied with high probability. There is a small chance of error, and again, you can reduce it as much as you want by repetition. So that's a probabilistic proof system. Every verifier, every probabilistic algorithm defines one. We have introduced errors in proofs, as I said, in the same way, but somehow, psychologically at least, it seems like a very different act. Proofs are holy in mathematics, errors are terrible in proofs. We try to eradicate them. So, that's a very bold action to make this definition, and we'll see the value of it throughout the talk. In the same way, we can define the sets computable or the sets acceptable by a verifier, so set of theorems of this system for every V. And now we call IP, for interactive probabilistic proofs, the collection of sets provable in such systems. Probabilistic I mentioned, interactive I'm going to explain in the next session, because the interaction between prover and verifier is slightly more general here. So what is it? What is an interactive proof? So remember, in NP, in the classical deterministic case, we had an argument sent by the prover to the verifier. It was a one-way interaction. In IP, which is probabilistic, we allow actual communication. So it's not just the prover sends an argument to the verifier can ask as many questions as he or she wants from the prover, and only then decide whether to accept or reject. So there is an interaction here. You may wonder, first of all, why not allow it in the deterministic case? Well, then it doesn't matter. It doesn't help or doesn't change the value. You may wonder whether this is a reasonable definition to allow interaction between prover and verifier, but given that we all experience it in the classroom, in seminars, I mean, it's a very interaction between mathematicians in the very nature of our work, it definitely seems a reasonable class of proof systems or arguments. And what I want to stress is that this definition is a revolutionary scientific notion. I mean, since its introduction, it's had a huge impact. I will not go into too many details on the scientific and technological impact. I'll tell you more about the first two, and in particular, how it leads to proofs that have paradoxical properties that cannot be attained by classical deterministic proofs. So errors give us something new. In particular, I'll tell you briefly about zero-knowledge proofs, convincing but do not convey information, and probabilistically checkable proofs, where you hardly need to know, to read the argument in order to know whether it's correct or not. So that seems, ridiculous, and we'll see it. But I more want to talk about this journey that led from zero-knowledge proof to PCP, which they seem unrelated, and also how we got from interactive proofs to multiple prover interactive proofs to the final quantum interactive proofs that I want to end with. So let's talk about zero-knowledge proof systems. Zero-knowledge proof systems are the same as proof systems, only you add another requirement. The requirement that if the verifier accepts, namely believes the claim, it learns absolutely nothing else but the fact that it is true, despite the long interaction and the many questions it asks. And this seems preposterous if you've never seen it. I want to stress that it's not trivial to define, but the intuitive meaning is enough for us. And, you should ask yourself, if you haven't seen it before, whether such a thing is possible. Is it possible to be convinced by some argument that gives you no information? you can think about particular claims, and if anybody could convince you that they can factor a large integer or prove the Riemann hypothesis without giving you any information. But, you know, life as it is, there are surprises. And a year later, we proved with Goldreich and Micali that under the most standard assumption of cryptography, that one-way functions exist, namely, for example, that factoring is difficult, NP, all of NP has zero knowledge proofs, which in plain words says that every proof you have, absolutely every proof of any mathematical statement you have, can be turned efficiently into a zero knowledge proof. Everything can be proved in zero knowledge. This had major impacts, both theoretical and practical, that I'm not going to. As I said, I want to talk about how it led to new proof systems, so let me do that now. Back to the theorem, I stressed that we are using the assumption of cryptography, and when we did that, we wondered whether this assumption is necessary. So whether you need cryptography in order to have zero knowledge proofs. And the answer, like many things in life, yes or no. I have a theorem with Ostrovsky that in this model of IP, it is necessary. You must have cryptography. You must have such an assumption. But, you know, as we often do in math, you can change the model. And in another model, its answer is no. So let me move to this new model. That was the very reason for introducing an extension of IP, multiple IP, many provers, and I'll focus on two provers. This was done in this paper with Benor, Goldwasser, and Kilian. It's the same game. The verifier wants to know something, but now he's interacting with two provers who are physically separated, and that's critical. The verifier can ask them both questions, and they don't see the questions to the other prover. They may have, conferred in advance to plan a strategy, but once the conversation with the verifier starts, they are in different isolated parts. And still, the same thing, the verifier has to, completeness and soundness have to happen with high probability. So it's another type of proof system. And in this proof system, we showed that what we wanted, zero knowledge, does not require any assumptions. So in somehow, the physical separation replaces the cryptographic assumptions used for the single prover case. This was the motivation for introducing MIP, and this was, we were quite satisfied, and that's roughly where I left this field just before it started to explode. So let me tell you about this explosion. You may ask beforehand whether it's a reasonable model, like we asked with IP. There are several answers. Certainly, police is using this with interrogating, several suspects who are suspected of together committing a crime, separating them and interrogating them. Another way to think that it's reasonable is the fact that the institutions we were at actually decided to invest money in patenting this. But anyway, mathematically, it's extremely interesting and very rich, as we'll see, so let me proceed. What we knew at this point was that we have a collection, sort of a hierarchy of proof systems, NP, IP, 2IP. And at the time, there were only trivial inclusions of the power, of the computational power of what they can, the type of claims they can prove. Things in IP were always computable in polynomial space. Things in 2IP were always computable in non-deterministic exponential time. These are very high classes, and nobody believed that they are even close. But, 2 years later, sort of an avalanche of characterization arrived. I'm not going to go to tell you the meaning of them. They have conceptual meaning, but I want to stress, first of all, that they characterize these classes. IP actually is equal polynomial space. Multiple IP is equal non-deterministic exponential time. And the final one, the PCP theorem, I will tell you about shortly. I want to stress also that in this, theorems, there are no assumptions, no cryptographic assumptions. So what is this PCP theorem? Again, the acronym stands for Probabilistic Checkable Proof. These are non-interactive proof systems, just like MP. So we have, again, the prover and verifier. They have a claim at hand, and the prover sends an argument to the verifier. And the added spice, the added condition, is that the verifier is allowed to read only, let's say, 20 bits of the argument, no matter how long it is. So to just demonstrate it, it seems ridiculous that anybody could discover a bug in a 100-page proof. And you can imagine that, somebody proved the Riemann hypothesis, probably written a mountain of books with 1,000 pages containing the argument for it. And we would like to check it, only looking at 20 bits. So what can be proved here? Well, again, despite how ridiculous it is, the PCP theorem says that everything in NP has such a probabilistically checkable proof. Every proof can be, of course, not the original proof, maybe, like with zero knowledge, but if you have any proof of the Riemann hypothesis, it can be turned efficiently into a, slightly longer proof, which can be checked in exactly this way, just by reading a constant number of bits with a high probability. So this would be a dream. If this were really practical, it would be a dream for refereeing. I mean, we would do it in seconds and not refuse to referee anything. Of course, the real value is in amazingly deep and important contributions to optimization, to coding theory, to complexity theory, that I will not talk about. And part of it can be actually be made efficient enough to be used in technological products that you are all using, in fact. But I want to go back to talk about the extension, the quantum extension, and the last breakthrough that I advertised in the title. So remember that we understood completely, we had characterized the computational power of these new proof systems with errors, interactive proofs with one prover and multiple provers. This is if we allow randomness and error. Now we are going to replace, or add rather, beyond randomness, we are going to add the quantum power. So again, as I am introducing quantumness into proof systems, I want to, before I tell you about quantum computation, as I did with randomness. So let's have a one-slide tutorial on quantum computing. Again, you start from the same observation. Nature seems to provide us access to quantum phenomena. Quantum mechanics seem to work in our world. And so again, why not use it in computation? This was suggested independently in the West and in the East. Let's build quantum computers that manipulate their objects according to quantum mechanics, and manipulate superposition using unitary operations, manipulate qubits. It took time to formalize this notion, to make it not as simple as formalizing normal computers, algorithms. But it was done, and we now have, like we have P and BPP for probabilistic algorithms, we also have BQP for quantum, efficient quantum algorithms. And so it went for a while until a bombshell landed when Peter Shor in '94 found out that quantum algorithms can efficiently solve both factoring integers and discrete logarithms. And of course, as you know, these are not arbitrary problems. These are the very problems whose assumed hardness underlies all security systems, all online shopping, everything in the current, current world. And so there became, frenzy attempts since then to develop many things. First of all, try to build quantum computers, build this technology. And so far, billions were invested in this, and some progress is made. There was attempts to, and they are ongoing, to develop post-quantum cryptography. Cryptography, a new hardness assumption that will be able to sustain quantum computing if it becomes available. People try to invent new quantum algorithms for new other problems, maybe for NP. Of course, there is no such progress so far, very few new problems of quantum algorithms. And the one I want to focus on is the development of new models in which we have the quantum power. And quantum proof systems are the ones I want to talk about. So what happens with quantum? The same, we add quantum power to the verifier. Of course, to the provers, they are infinitely powerful, so you don't need to add anything. So let me explain this. Tell you the history. In 1999, what was introduced quantumness to the one-prover proof systems, and this is called, we add star to denote quantum. And people, that's again with this methodology of trying to understand the power of proof systems computationally, what complexity theories do as instincts by now. It took about a decade to show that actually adding the quantum power in interactive proof with one prover does not add any power. It's the same as the classical interactive proofs, just p-space. Then people introduced quantumness to many proof systems, MIP star, and here the story was even more, amazing. Again, it took some time, almost a decade, to just prove that it's at least as strong as the classical MIP notion, because both the verifier and the prover get extra power here. But this was done. Everybody expected that, again, there'll be equality, that quantumness does not add power. But like 7 years later, it turned out that, you can do more. You can do this non-deterministic double exponential time is exponentially more powerful than just exponential time. So it became clear that MIP star is stronger than MIP. And the culmination of this was in this breakthrough of G et al., that MIP star equals RE. Namely, if you remember from the first slide, RE is a class that Turing defined, which is a recursively enumerable sets which contain uncomputable problems. So quantum proof systems can prove uncomputable problems. Totally surprising everybody. But the surprise, within, let's say, computational complexity, theoretical computer science, maybe quantum information theory, this was not the end of the story, because this result is so deep that it implies many other results in mathematics and physics. It provided counterexamples to very famous conjectures in quantum information theory to the Tierson problem, in von Neumann algebras to the Cohn's embedding conjecture, in group theory to the Kirchberg conjecture, and I'm sure many more will be found. I'm not going to explain this, but just saying something. The nature of the result deals with the power of measurements on large Hilbert spaces, and in one word, that's the connection to these various subjects. I want to explain more about the nature of this quantum interactive proofs with many provers, and how they relate to classical questions almost century old in the foundations of quantum mechanics. So for this, it turns out that it's sufficient, and it's sufficient, in fact, in general, to look at just one round proof systems, just one question and answer, which lead to the point of view of proof systems as games. what do I mean by a game? So here, let's go back to the classical two-prover setting. We have this picture. The verifier asks one question of each prover, gets one answer, and then decides to accept or reject. Well, what do we mean decide? I mean, randomness of the questions are generated at random, but at the end, the verifier has a function and evaluates it. So we can, whether to accept or reject a claim is decided by whether this number is large or small. So let's define the value of this game to be the maximum probability that this verifier accepts given the questions and answers, under the best strategy that the provers could have devised ahead of time. Okay, so that's a number between 0 and 1. It's a probability. In contrast, by the way, this doesn't change even if the provers have access to a common random string, not communicating, but just access. In the analog, in the quantum analog, it's the same picture, only that now the provers have access to a quantum state, to an entanglement. I realize not everybody knows what it is, so I'm sorry about that. But the quantum analog of a random string is a quantum state. And we can define another value, what's the maximum probability that the provers can convince the verifier now with this extra power to accept the answers they give to the questions. In computer science, we study, just the complexity of computational power of this system, so just how hard it is to approximate these values. That's another view of what we've seen, and we've seen these characterizations. But this one-round, proof systems or games, if you, stare at them, and this was already understood when MIP star was defined, they have appeared in physics many, many decades ago. Here at the institute where I am, Einstein with his postdocs, Podolsky and Rosen in 1935 introduced his famous, Gedanken experiment to test quantum mechanics. If you squint at this picture here, you may see a two-prover system. You may see two provers, these detectors at both sides. And so the claim is just, the source generating two photons traveling at the speed of light opposite from each other after generated by a single event, so they are entangled. And they proposed it as a way to test quantum mechanics. In the language of physics, the top case is called the classical or a local game. And the random string is called hidden variables. These are hidden variable models for those who have. In the quantum case, it's called a non-local game. And what may be called the spooky action at a distance that Einstein didn't believe in, because it seems to violate the speed of light limitation. And they mainly designed experiments in which the quantum value was bigger than the classical value to show that it doesn't make sense, or you at least have to explain it. And that was really the question: is quantum mechanics complete? That was the challenge in these experiments, and a sequence of very important influential works designed more and more examples within the realm of physics and from quantum information theory. More examples in which indeed the quantum value was larger, and eventually it led to such efficient tests that they could be implemented and actually confirm in the field, in the world, that quantum mechanics, the predictions of it at least, work. The meaning is still debated even today. On the computer science side, the paper I told you introduced MIP star, looked at things the way we always look at in complexity theory. It suggested to build the class of study together all non-local games, not necessarily those implementable or those that come from physical consideration, just in the abstraction, as we did with other proof systems. And it is critical that this allows the use of the tools of complexity theory, of reductions and amplifications and completeness, and actually some tools that were used beforehand for some of the previous results of PCPs and codes, in order to arrive at this result of MIP star equal RE, namely understanding the full power of these two-prover quantum proof systems, and via that arriving at these amazing consequences in mathematics. To summarize, what have we seen? We've seen a lot, and maybe at high speed. We've seen lots and lots of proof systems, and we've seen the evolution of the nature of proof systems, especially after we allow randomness and errors and then quantumness into proof systems, but stressing that in all of them, the definition insisted that the verification process is efficient. So even for this latest result, verifying an uncomputable function is done by an efficient verifier. We saw that allowing interaction and randomness and errors in proofs lead to proof systems with paradoxical properties like zero-knowledge proofs or these probabilistically checkable proofs that do not require you to even read most of the argument given. Something I like to stress again and again, theoretical definitions, starting from Turing definition of an algorithm, this Turing machine, and many of others we've seen, both predates and enables practical developments, and then of course also scientific and mathematical and societal ones. I hope it was clear the importance of the complexity theoretic methodology of modeling classes of problems according to their computational complexity and algorithmic efficiency, and the use of these tools that are repeated all the time, reductions and completeness and classification in building up these theories and these characterizations. Finally, something I didn't get a chance to talk much about, but there is a lot of interaction between different subdisciplines. You saw it mainly in the last slide about the impact of this result MIP star equal RE on physics and mathematics, but I also mentioned earlier the connections to coding theory and to optimization, although I didn't explain it. So this it's a very, I would say, interactive discipline. The algorithmic point of view connects to lots and lots of other fields, and this cross collaboration, just amplifies both the use and the progress of these fields. So again, let me end up by noting that you can always look for more in this book I wrote a couple of years ago on complexity theory, and it's available freely on my website. Thank you very much.
Well, thank you, Avi. Thank you very much for your wonderful and interesting lecture. We will start off with some questions. So some of the young researchers already asked questions during your talk. And there, two questions will go in the direction of applications. So let me start with one of them. So it's the question.
I don't hear you well, Anna.
Okay,
I don't hear you well.
Do you hear me better now?
Yeah.
Okay, good. So let me start with one question which goes in the direction of applications. And so there was one question, what would you think are the areas where these probabilistic proofs will be mostly applied, or find most applications?
So we keep being surprised when we develop zero-knowledge proofs. We were sure that they are too complex to be implemented anywhere. And it took maybe 30 years, but we were proven wrong and people could implement them. The there are so many uses already of applications of these probabilistic proofs. I mentioned one that everybody is familiar with, just doesn't know that that's where it came from, you know, or that it's used, cloud computing. I mean, you keep, your cell phone does so many things for you. It computes so many things, but of course it doesn't do it really, right? I mean, it's not done on your cell phone, it's done somewhere in the cloud, in some powerful server. Well, how do you or your cell phone know that the computation done was correct? I mean, how do you verify in cases where it is important? Let's say verify that it reads your login, your password as it should, and so on. These are interactive proof techniques. I mean, that's a very basic use of interactive proofs. Interactive proofs are used now routinely in a variety of digital currencies that are available. They heavily use ideas from PCP technology, for example. So there are so many, and I wouldn't be surprised of seeing newer and newer ones. It's a very basic fundamental concept, and allowing errors in this type of proofs is, of course, extremely natural. It's not that you will not know the value of the Riemann hypothesis, whether there's some chance. Of course, we know that in real life proofs there are also errors, and sometimes they are not discovered. But here, errors are actually robust and can be reduced arbitrarily, so there is value in that too.
Well, great. A question which goes in a slightly different direction. Would you say that the current state of the art of the PCP proofs are somehow enough for applications, or also should develop further to somehow bring out more applications?
No, they are, as I mentioned just now, they became practical enough to be used in digital currency technology, where you need speed, you need to do maybe thousands or millions of transactions a second. Of course, they improved practically in an amazing way. But yeah, there's always room for more.
Yes, yes. So here's another question from the young researchers. So we now have quantum computers with about 66 qubits. How strong must a quantum computer be to realistically implement quantum-proof systems for typical problems where you would like to apply them?
Well, it depends what the proof system is trying to prove. For proofs that quantum mechanics work, like these particular games starting from Einstein and Abel inequalities, you don't need a quantum computer really. You just need something much smaller. When people talk about building quantum computers, they talk about general purpose quantum computers. And if you want to be able to make the computations, let's say the Fourier transforms, the quantum Fourier transforms used in factoring algorithms, or whether the claim you want to prove, has such a component, this requires general purpose computation, and yeah, we are not there yet. I have no idea. I mean, you should ask Scott Aronson when he gives his lecture. He knows much more about the practice of quantum computers.
Yes. Let me come to one other point of your lecture, which you highlighted also in the summary, and which for me really is a wonderful example in your talk about the interaction between the different fields, and also between somehow questions coming more from computer science and somehow then having an influence on mathematics, and even giving counterexamples to somehow long-standing conjectures in mathematics. So in this, I mean, from the result, this MIP star equals RE, do you expect more applications within mathematics then?
Yes, I certainly do, but the point is far more general. Having now experience of some decades and seeing many, of course, this is not the first result to have
Yes, sure.
applications in mathematics, and of course vice versa, but there's a fundamental point that in mathematics, I mean, there are several of this nature, but let me tell you one. mathematics has lots of existence theorems. You prove that something exists. The complexity theoretic message is, okay, it exists. How long does it take to find it? When you just ask this question, you are led to doing far deeper mathematics on the same question that you looked at. And this was done, of course, was done by mathematicians, even before complexity theory existed. But now, with the interaction of complexity theory and math, we see applications in algebra, in topology, in group theory, in geometry. Anywhere you look, there's connections like this. So this MIP star equal RE is just one particular striking example of the connection between the algorithmic point of view here in the context of proof systems and mathematics.
Yes. So I have one other question which addresses the axioms you made. So for example, already in the non-quantum probabilistic proof systems, you started with the axiom that randomness is always there, given to us by nature. But of course, it's not that easy, I think, in general. So is there, could you comment on that, perhaps?
Yeah, I can come. What do you mean I can come? I can give a separate lecture on this, and I haven't.
Yes.
It's a beautiful field. It's probably the area to which I devoted most of my time in the last few decades, understanding the power of randomness and what do we do if nature does not provide us with randomness at all, or maybe it provides us not with pure randomness, but rather weak randomness with just some entropy, but not very structured, like independent, unbiased coin tosses. And there are beautiful theories in computational complexity which tell you, what you can do in this situation. So, I'll tell you one theorem because I like it and because it's, I was involved with it with Russell in Pagliazzo. If you believe that P is different than MP, okay, there is an assumption of this nature. If you believe it, then randomness is not needed in probabilistic algorithms. Probabilistic algorithms can be replaced by deterministic ones without error that are as efficient. So we have connections between randomness and computational difficulty. And this is just one example. So we have a lot to say about about randomness. But it's certainly an assumption for probabilistic algorithms that you have access to such pure random coins. And you are absolutely right that there is no real reason to assume it, which is why we study what we can do without it. Yeah.
Yes. So thank you. So there's one other question raised in the chat that, I mean, the applications you described by probabilistic proofs are in some sense really important and touching our society. So do you think that there's some responsibility also in developing those, or special responsibility researchers should take?
There's always responsibility, and with everything you discover, I'm sort of a believer that technology and ideas cannot be stopped. And the important role is for the society to have good use of technologies. Of course, it's much more benign than nuclear power and nuclear bombs and so on. But I agree completely. Responsibility is important. I want to maybe mention one area where demonstrates the responsibility of computer scientists in this development. Now that artificial intelligence is entering all parts of society, and in particular decision making by judges, by bank officers, by parole officers, by practically everyone, that these algorithms will be fair. And the very definition of fairness, which is something that, of course, philosophers and social, academic world looked at, become newer through definitions that are coming from an algorithmic point of view. So lots of my colleagues are doing that. So I think you see the responsibility is taken automatically, and probably partly because it's also intellectually challenging and interesting, and beautiful things already came out.
More technical question. I mean, you went from one prover to having multiple prover, which really changed the game in a sense. So one young researcher is asking whether you could also change the game by introducing multiple verifiers, or would it just stay the same?
Yeah. So the question is, what would you define as the set of theorems in that system? The fact that you can ask this question, and you have to say, well, is it something that both verifiers are convinced of, or only one of the two, and so on? But it's not clear to me that this will add something new. I can't say I thought about this, but it's it depends what you want to do with these two verifiers. It's clear what more provers are doing. They can do different things. Verifier, all the verifier wants to know is whether the claim is true. I would assume that more verifiers would want to know the same. I mean, of course, you can just take the existing definitions and allow more verifiers in it, and it won't change. But maybe you are thinking about more, different definitions. I don't know.
Yes, thank you very much. So perhaps in the last minute we have, can you give us a glimpse in what is the somehow most important or interesting problem you are currently thinking about?
P versus NP. I've been thinking about it all the time. I think about it in many different ways. And the last 5 years, I'm mainly spending time in trying to understand or hopefully prove, but I don't know, an algebraic version of it. This is called the VP versus VNP question, V for Valiant, to introduce this. So trying to prove that in the algebraic setting, when you do addition, multiplication, as opposed to Boolean operations, P is different than NP. And this has amazing connections to invariance theory, at least the route that we are taking, amazing connections with invariance theory and algebraic geometry, and really cool stuff. So I'm learning a lot. That's a summary of it.
Thank you very much. And let me just say that, I mean, to the young researchers, you have the opportunity to sign up for laureate group discussion with Avi, and you will also see Avi again in a laureate discussion later this week. So if you still have questions, you can try to catch him and ask your questions in these other formats. Thank you very much, Avi. It was wonderful to have you, and see you later this week.